So hello guys, today we're going to be doing chapter 10 hypothesis testing. So first I just want to just make an example of what a hypothesis is. So it is a premise or claim that we want to test. So let me highlight that. So it's very important that we want to test it because we want to know if our hypothesis is true or not. So when you have hypothesis, you can either have your null, which is categorized by HO over here. I'll highlight that in green. And it is the currently accepted value for a parameter. So alternative, which is HA, let's see the red now. I'll do, well, you guys can see I'll surround it in red. HA, alternative is HA, and it's just the opposite nature of our null hypothesis. So for an example of how our solar system worked in history, well, our null hypothesis back in the day was geocentrism, which was that Earth was at the center of our universe. And so that was the believed idea of how our solar system worked, and we had no way of testing it if it was true or not. So when heliocentrism came out by Copernicus, which is our HA in this case, well, he believed that the sun was at the center of our solar system. And when he did tests, and scientists did tests to see if this was true, they figured out that heliocentrism was the correct form of system for our solar system. So this is an example of how null and alternative works. So I'll give another example using numbers, and this will apply to more the problems that we'll see in the future. So a candy machine makes chocolate bars that average 5 grams. A worker claims after maintenance the machine no longer makes 5-gram bars. So write HO and HA. So what you could see from HA is that our average is equal to 5 grams because in the first sentence, a candy machine makes chocolate bars that average 5 grams. But alternatively, a worker claims after maintenance the machine no longer makes 5 grams. So in our alternative HA, we have our average, which is U, no longer or does not equal to 5 grams. And what you can decipher from HA and HO is that it will always be exactly opposite of each other. So here you see that U is equal to 5 grams over here, and that our alternative, which would be the opposite, sorry, I didn't mean to highlight that. Let me write that back. So our U it does not equal 5 grams. So another example is if our HO is U less than 10 grams, our HA has to be the opposite. So U would be greater than 10. So that's pretty much how our null and alternative hypothesis works. So when we're dealing with null and alternative hypothesis, we have two types of errors. So we have a type 1 error, which means rejecting something that is true. So that means if, and we call this alpha. So if we reject something accidentally, like we're not doing it on purpose, but from our testing, we reject it, but it ends up being true, that would be called a type 1 error. And a type 2 error will be accepting something that is false. So that means there was a problem in the way we tested something, or I guess in our confidence interval, that we accepted something that is in fact not true. So we shouldn't have accepted it. So that's why they're called errors. And so another idea is if the sample falls into A, which is our alpha, which is also the result due to chance, we must also reject the hypothesis because we can't accept a hypothesis due to it being by chance. It has to be scientifically proven and like not due to chance, but with reason and scientific information. Alright, so I'll be explaining critical values and p-values. So starting off with critical values, well, it is the region to reject the null hypothesis. So in this normal distribution, let me get my black pen. You could see that the normal distribution that I made, you could see that the region to reject the null hypothesis is in red over here. And so if z-score falls into the red area, which is our critical value, we must reject our null hypothesis. The critical value with 95% confidence level is 196. So like in this example, it took 95% confidence level. So negative 196 and 196. Critical value of 99% is negative 2.576. Let me just highlight that for you. So it's this and this. And critical value of 90% is this and that. So as you guys can see with the numbers, if your confidence level is smaller, your intervals are going to be smaller. So for example, comparing this so I'll use the 90% confidence level, comparing it to the 95% confidence level. So our critical value on the left side is negative 1.645. So I guess it would be like around here. I should do that in red actually. So I just want you guys to visualize like what a 90% confidence level would look like compared to a 95% confidence level. So it'd be negative 1.645. And then I'll just do it here. Just pretend like it's symmetrical, 1.645. And as you could see that, and if I color this in like that, our region to reject the null hypothesis, so our critical values is a lot bigger. So that means we have more possibilities to reject the null hypothesis. And yeah, so just pretty much like the higher your confidence level, the better it is to make sure what you're doing is correct. So that just shows the importance of a higher confidence level. So going on with p-values, well, it's the probability to reject the null hypothesis. So p-values and our critical values are just ways that we could use to reject the null hypothesis. And you can use either or, just depending on your scenario or what you prefer. So in some cases you might use your critical values, and in some cases you might use the p-values. So here, found from the z-score, area of that z-score. So in this normal distribution, and I'm using a 95% confidence level again, let's just say that when we calculate our z-score for an example, it gives a z-score of 2.31. So once you look into the z-table, so first you find the z-score, then you find the area of the z-score. So you can find the area of the z-score by looking for this number. So look for 2.31 in your z-score table, and that should give you around, let me get my calculator. It should get you like 0. Let me just do it real quick. So it should give you, if you look at the table, it should, let me get the black pen. It should give you 0.98956. So that would be everything to the left of here. So it'd be like all of this. That's what 0.98956 would represent. But since we want everything to the right, which is pretty much this, we just do 1 minus 0.98956, and that equals to 0.01044. And so that is our p-value, because yeah, it's pretty much the area of the z-score. So once you find that, you want to check if your p-value is less than alpha. So if your p-value is less than or greater than alpha, we must reject the null hypothesis. And if the p-value is greater than alpha, we must accept the null hypothesis. So in this example, again, our p-value is 0.01044, and our alpha is going to be 0.5. Is it 5 or 0.5? Yeah, I believe it's 0.05, because this is 5%. So you know it's 0.05 because your confidence level is 0.95, and then this adds up to 100, or 1, I should say. 1. So yeah, that's how you know what your alpha is, and then that's how you pretty much find out what your p-value is. Okay, so this image is to help you visualize or kind of see which way you want to approach between p-values and critical values. So as I said, it doesn't really matter. It pretty much gives you the same thing of figuring out if you want to reject or accept your null hypothesis. So once you find you want to state the null and alternative hypothesis, you want to choose your alpha, where you find your alpha, you calculate your test statistic, which I'll explain later, which is either your z-score or t statistic. So from that, you can find your p-value approach or your critical value approach, which some people like to say the classical approach. So yeah, hopefully this image helps you guys visualize or understand more how to use their p-value compared to critical value. Alright, so I'm going to be explaining z-tests about a population mean when our standard deviation is known. So z-test is finding the z-score to compare with the critical value. So using the formula, let me highlight it for you guys. Z equals to x bar minus our mean, which is u, divided by our standard deviation of the square root of n, which is our sample. So using this formula, we could check if the z-score falls inside the critical value. Yes, let me just do an example here on the side. I'll draw one out. So here, let me just draw a normal distribution. And so if our critical value, let's say for 95%, I'll do it right on top, 95%, it's over here, and then over here, 1.96, negative 1.96. This is always going to be the same. Negative 1.96 and 1.96 is always the same. That's our z-score for a 95% confidence interval. If your z-score falls between here, if it falls inside this or in here, we must reject our hypothesis. So yeah, so you pretty much, if your z-score falls in between the red, you reject your null hypothesis. Alright, so going on with the t-tests about a population mean when our standard deviation is unknown. So we use t-tests if our sample size is less than 30 and if our standard deviation of the population is not given. So the first step to do is to find your alpha. You could do this by finding your confidence interval. Usually it's, well, most of the time it's given. So your alpha, and then from that you could find your degrees of freedom, and degrees of freedom is equal to n minus 1. Let me just highlight that for you guys. You guys can see degrees of freedom is n minus 1. So the third step is to find your critical t value, and that's by looking at your t table using using both your alpha, so using both the alpha and degrees of freedom, you could find your critical t value in your t table. And then fourth step is to find your calculated t value with the formula of t equals to x bar minus the mean divided by your sample standard deviation divided by the square root of n. And then from this you can reject or accept the null hypothesis. So if your calculated t value is inside your critical t value, well then we must reject our null hypothesis. And if calculated t is outside our critical t value, we must accept our null hypothesis. So for an example here, if I have a normal distribution and we're going to have only a left-tailed alpha. So if our critical t value from what we calculate is negative 2.82, so yeah, and then once we find our calculated t value, which is negative 4.22, we can realize that on the normal distribution it is in our blue area and it's inside our critical t value. That means we must here, as I already, reject the null hypothesis. So hopefully you guys can understand when to use t-test or z-test and how you can apply it to our questions and how we can reject or accept our null hypothesis. We'll be talking about the steps to solve any hypothesis question. So the first step is to state the null hypothesis. So I'll do that in green. And the null hypothesis is the current and accepted claim in the moment. So then step 2 is to state the alternative hypothesis. So this is the alternative claim. It's a claim that is opposite of your hypothesis. So I've stated what null and alternative is before in the video. So hopefully you guys know what those are and how to distinguish it. So the third step is to identify significance level alpha. So your alpha is the area of or region where we would reject HO. So your alpha is equal to 1 minus the confidence level. And our confidence level is usually 99%, 95%, or 90%. So the step 4 is to identify which model to use. So you have 3 models, your z-score model, the t-table, and the proportion model, which is kind of using the z-score, but in a different way. You're using proportions instead of means and values. So step 5, to find your find your critical value. So highlight that. This is an important part. So find your critical value. And so the critical value is the cutoff region that separates your rejection area and the acceptance area. So yeah. So first, the z-score critical value and the proportion critical value, they use the exact same way of calculating the critical value. So if you're given a 99% confidence level, your critical value will be negative 2.58 or 2.58, or sorry, and 2.58. That's assuming that you have a two-tailed test to do. So as you can see right under the diagram, the red region is your cutoff, which is the rejection area, and your critical value of negative 2.58 and 2.58 separates, it's pretty much the line that separates it. So if you're given a 95% confidence level, your critical value will be negative 1.96 and plus 1.96. So again, assuming that you have your two-tailed test. Let's say if you have only a one-tailed test and it's to the right, well, it'll still be 1.96, but you wouldn't include the negative. And it's the same thing if it's a left tail test, you would include your negative 1.96, but you won't include your 1.96. But it would still be the same, the critical value would still be the same. Alright, so if you're given a 90% confidence level, your critical value is negative 1.645 and then 1.645. So as you can see, with all the critical values, they're all, let's say for 99, it's the same number, both negative, but the reverse would just be positive since it's a normal distribution and everything is symmetrical. So yeah, that's your critical values for your z-score, and it's also the critical value of your proportion method as well, since they both use the same z-score thing, z-score table. So number 2, it's the t-table critical value. So the first thing you want to do is to find your alpha. As I've mentioned, alpha is 1 minus your confidence level. So then second is to find your degrees of freedom. So your degrees of freedom is n minus 1. And now your third step is to check the t-table. So like I said, let's say if our A was 0 and we have a two-tailed test, our A is 0.1, or it would be, it's the same thing as saying 0.05 for a one-tailed test. And so on the left, we have our degrees of freedom over here. And all you want to do is find where the two meet. So they both meet at 1.812. So that would be our T critical value. So now step 6 is to find your calculated value. So I'll do that. I'll highlight that for you guys. Calculated value. And so number 1 is the z-score calculated value. So this is the formula for z calculated. It equals to x bar minus ux divided by your O, which is standard deviation, divided by the square root of n. So x is just a given number, or it's a given mean. Your u is the mean that your population mean. Your O is your standard deviation, and then n is the sample size. So x could also just be a number, and then u would be your mean. So to your t-test calculated value, so what's highlighted in orange is your formula. So t calculated is equal to x bar minus ux divided by s divided by the square root of n. So if you guys are wondering what's the difference between this and the z test for a calculated value, is because we have our s here. So I'll highlight that in orange. So what's in orange right now that I'm highlighting is your s, and that's your sample standard deviation. So we use our t-test when we don't know what our standard deviation is, and then we use our z-test when we do know our standard deviation of the population. So t-test is the standard deviation of a sample, O is the standard deviation of the population. So like what's written here, S is sample deviation, UX is the mean, and X is the given number, and is still the sample size. So 3, your proportion calculated value. So what's highlighted in green? So it's the formula is Z is equal to P hat minus PO divided by the square root of PO times 1 minus PO, or Q. So 1 minus PO can also be referred to as Q, and it's just the opposite of PO, divided by n. So what's here is p hat is the sample proportion, and you can find p hat by x divided by n. So the number divided by your sample size. PO is your population proportion, and then n is your sample size. So 7, this is the last step, accept or reject your null hypothesis. So the reason to do this, or how to do this, is you want to compare your calculated value and your critical value. So what I like to do is to draw a graph with critical values and calculated values. So as we can see here in the graph, your critical value, let's say over here, this should be a negative. Don't want to confuse anyone. I'll put negative right here. So negative 1.96, as you can see, it separates the area. It's the line that separates the area from the white space and the red space, where the red space is your rejection area. So if we look on the right side here, I have our calculated. So let's say I put random numbers and I get my z-score. This is a z-score graph. Let's say my z-score that it's calculated equals to 1.56. And once you put that in the graph, we can see that 1.56 isn't in the red zones, any of the red zones. So that means that we accept our HO, our null hypothesis. So if your calculated value does not, so I'll write that, and I'll put that in green, so it does not fall into or does not pass the critical value, this means you accept HO. But if your calculated falls into or passes the critical value, this means you must reject your HO. Alright guys, so I think that's it.